Today, we are going to do a little time traveling. We're going to use a single academic paper from 1994 as our guide. And trust me, it's a wild ride. It's a story about a problem, a researcher, and a solution that seems almost quaint now, but it shows just how radically our world, technology, software, science, all of it has changed. It's a great reminder that the tools we have don't just help us find answers, they actually shape the kinds of questions we can even think to ask in the first place. All right, let's get into it. Okay, just look at this for a second. This is from the paper we're talking about. It's the program availability section. Now read that last sentence. Users who want to obtain the program should send a blank formatted 5.25-inch diskette and a self-addressed stamped envelope to Herman Aguinas. Let that sink in. To get the software, you had to physically put a floppy disk into an envelope, stick a stamp on it, and mail it to the guy who wrote it. No joke. This one sentence is our wormhole into a totally different world. So, you might be asking, why would anybody go through all that trouble? Mailing a floppy disk? Well, it's because researchers back in the early 90s were kind of stuck. They had these huge, complex questions they wanted to explore about, human behavior and social systems. But the tools they had on their desks, they just weren't up to the task. I mean, you have to remember, this is 1994. The World Wide Web was just becoming a thing, and for most people, it was that awful screeching sound of a dial-up modem. The idea of downloading a program in seconds? Pure science fiction. Sure, powerful computers existed, but they were these giant mainframes locked away in university basements. They were basically inaccessible monsters you needed special permission and a big budget just to look at. And this created this massive gap. On one side, you had the mainframes, super powerful, but behind lock and key, expensive, and a real bottleneck for getting research done. But on the other side, the personal computer was suddenly everywhere. It was on almost every researcher's desk. So what they desperately needed were tools that could run these sophisticated simulations right there on their own PC. They needed something that could finally unlock all that potential just sitting on their desks. And this wasn't just some small inconvenience. This quote from the paper itself really lays out the tough choice they had. If you wanted to do this very specific, very important kind of data simulation, you had two options. Either go through the hassle of getting time on a mainframe, or you had to dumb down your research. You had to limit its scope, its ambition. It was a terrible trade-off that was literally holding science back. Well, all that frustration led to a really brilliant solution. It was a simple program designed to bridge that very gap, running on pretty humble hardware, and it was available to absolutely anyone for the price of a postage stamp. It was this act of scientific generosity that honestly had a huge impact. So here it is. This is the paper that held the key. It was published in the journal Educational and Psychological Measurement. And in it, a researcher named Herman Aguinas didn't just complain about the problem, he actually offered up a working tool to solve it. He wrote a program that could do these complex simulations on a basic, everyday personal computer. The specs here really tell the whole story. It was written in QuickBASIC 4.5, a pretty accessible language back then. It was built for a standard 386SX Office PC, not some supercomputer. What did it do? It ran complex Monte Carlo simulations. And the cost? Free. This wasn't some commercial product. It was a tool for the whole community, for any researcher who had a PC. So what in the world is a Monte Carlo simulation? Well, basically, it's a way to create thousands of artificial but really realistic what-if scenarios. It lets researchers generate simulated data so they can test out their theories before they spend a ton of time and money collecting real-world data. It's an incredibly powerful way to understand complex systems. And that's the real kicker. This program took a capability that was mostly trapped inside those expensive, hard-to-access mainframes and put it right onto a regular old desktop PC. It was a democratizing force in science. It leveled the playing field, It empowered grad students, professors at smaller colleges, researchers without big grants. Suddenly, they could all do this high-level simulation-based research. So, how did this little program actually pull it off? Understanding the basics shows just how elegant and efficient this solution really was, especially for the kind of hardware it was running on. Okay, here's a quick analogy. Let's say you want to simulate a population. You know from real life that things like height and weight are related, right? Taller people generally weigh more. You can't just create random numbers for both because the data would look totally fake and be useless. Well, this program was the magic ingredient that made sure all those variables were realistically connected, just like they are in the real world. It all broke down into 4 simple steps. First, the user would input what they needed, something like, hey, I need data for 10,000 people and I want height and weight to have this specific relationship. Second, the program would factorize that input. Basically, it created a mathematical recipe for that exact relationship. Third, it would just generate a big pile of raw random numbers. And finally, in the output step, it would take the recipe from step 2 and apply it to that pile of random numbers, shaping them into the final, realistic, and beautifully correlated data. And what did you get at the end of all this? 2 simple text files. Data.out had all the raw, simulated data ready to go. And stats.out was like a little receipt. It was a summary file that proved the data you got had the exact statistical properties you asked for. It was simple, it was effective, and it was so powerful. All right, let's zoom back out. The program itself is really cool, but the story around it, how you got it and what it ran on, that's what really shows us just how far we've come. That whole distribution method, a floppy disk in the mail, it feels like a relic from another civilization. And don't forget, this was all running on a 386SX microcomputer. The phone you have in your pocket right now isn't just a little faster. It is orders of magnitude more powerful. It's almost not even comparable. And that just shows the kind of ingenuity and clever programming it took to make sophisticated tools work on the severely limited computers of the time. And that brings us back to this incredible sentence. This physical, analog way of sharing code, it feels ancient. But in 1994, it was a perfectly normal, practical solution. It was a system built on trust, a handful of postage stamps, and just being patient enough to wait for the mailman to show up with your new software. This table just puts the change into stark perspective. Look at this. Acquisition went from mailing a floppy disk to type in pip install and getting a tool in seconds. The hardware went from a clunky desktop PC to a laptop or even the infinite power of the cloud. The software itself went from a standalone program to being a tiny part of these huge libraries in languages like Python and R. And the cost? It went from a postage stamp to just free, part of a global open source community. I mean, the speed of this change has been just breathtaking. We went from mailing floppy disks in '94 to maybe downloading a .zip file from some professor's personal website by the late '90s. Then came the first real code repositories like SourceForge in the early 2000s, which felt revolutionary. And now we have these massive interconnected ecosystems like GitHub, where sharing and collaboration are instantaneous and global. The journey from a floppy disk to pip install is basically the story of how the internet completely changed science. So all this leaves us with one last kind of mind-bending question. All the tools we take for granted right now, the Python libraries, the cloud servers, the instant collaboration on Slack or Teams, they all feel so permanent, so essential. But this paper is the perfect reminder that they're not. So what part of our modern workflow, the thing you use every single day without thinking, is going to look as quaint as a floppy disk in the mail 30 years from now? What tool do you use that will be tomorrow's time capsule?